Happy Friday, everyone. Hope you're doing great. Listen, today we're going to dive into one other aspect, building on what we learned yesterday, and that is with covalent bonds. Sometimes we have what we call polar covalent bonds and nonpolar covalent bonds, or we form what we call polar molecules and nonpolar molecules. And so today we're going to investigate that a little bit. To kick us off, I'm actually going to show a quick little video clip that I think is done well, and we won't see all of it, but here's a little crash course on polar and nonpolar molecules to get us started.
Molecules. So many of them in their infinite and beautiful variety, but while that variety is great, it can also be pretty dang overwhelming. And so, in order to help this complicated chemical world make a little more sense, we classify and we categorize. It's our nature as humans, and it's extremely useful. One of the most important of those classifications is whether a molecule is polar or nonpolar. It's a kind of symmetry, not just of the molecule, but of the charge. It's pretty easy to see when you're just looking at them. You got polar and nonpolar, polar, nonpolar, polar, nonpolar. I'm going to take sides right now. I'm on team polar. I think polar molecules are way more interesting despite their wonky, off-balance selves. Nonpolar molecules are useful and their symmetry has a kind of beauty, but polar, in my humble opinion, is where it's at. All right, now here are two very different types of chemicals. Right here, I have a stick of butter, and then in this bowl, that's just normal water. So I'm just gonna go ahead and squeeze this butter, which, if you're wondering, is both a terrible and wonderful feeling. And then I'm going to just drop that. Now I'm going to attempt to wash that butter off my hand, but that is just not it's not going anywhere ever. It's just beating up on me. Why? Because water is a polar molecule and the various chemicals that make up butter are nonpolar, and water wants nothing to do with that. So, what makes a molecule polar? Well, two things. First, asymmetrical electron distribution around the molecule. You can't have a polar molecule made up entirely of the same element because those atoms will all have the same electronegativity, and thus the electron distribution would be completely symmetrical. Electronegativity is usually thought of as how much an element wants electrons around it, but I think it's more about how much electrons want to be near that element. If electrons were 13-year-old girls, fluorine would be Niall Horan. They'll do anything just to be near it. Why? Some simple periodic trends. Electronegativity increases from left to right because there are more protons in the atoms, and more protons means more boys in the band. Meanwhile, it decreases as you move from top to bottom because as the crowd of electrons gets bigger, they start to shield each other from the effects of the protons. What I'm trying to say is that electrons are hipsters. If a bunch of other electrons are into that thing, they're less interested. Now, there are a number of other factors here, but just like the relationship between tweens and their latest boy band fixation, it's complicated and weird, and you probably don't want to think too much about it. But in this nice little map, you can see that the trend is pretty clear. The upper right is where all the superstars of electro fame are. Oxygen, nitrogen, fluorine, chlorine, and bromine are basically the one direction of the periodic table. So for polarity to occur in a molecule, you have to have two different elements at a minimum, and the difference between their electronegativities has to be 0.5 or greater. If that's the case, the outer electrons spend enough extra time around the element that's more electronegative that chemists label the molecule polar. The result is a partially negative charge on the more electronegative part of the molecule and a partially positive charge on the less electronegative side. Now,
Wow. What do you think of that? It's good stuff. I do think he probably goes a little fast, and there are a few things that maybe were a little bit over our heads yet. And so I'm going to try to walk you through a few items that hopefully will clear it up. We'll go a little slower, but some good stuff in there in terms of setting the table for what we're going to do, because absolutely right, it has to do with having a molecule that's got a positive end and a negative end. And so when we talk about polar molecules and nonpolar molecules, just like the Earth has its north and south poles, polar molecules will have one end and another end. The difference being, instead of north and south, we're going to be talking about positive and negative ends of their poles, positive and negative sides. And he threw that word electronegativity in there, real fancy, big word. But what that really is saying is that how much pull does an atom have on an electron? How strongly is it pulling on an electron? Sometimes there can be kind of a mismatch, uh, much like these little girls pulling against the army squad in a tug of war. Okay. Other times, not so much. It's going to be a little bit more balanced. And so that's what we're going to look at because that is what's going to cause something to be either polar or nonpolar. A polar covalent bond means, again, they're sharing electrons. Here you see the hydrogens coming towards the oxygen in the first part. And then they're going to be sharing those electrons. The difference being in a polar bond, okay, the sharing is not going to be equal. Okay, oxygen has a higher electronegativity, as was mentioned before, than hydrogen. It's got a greater pull on that on those shared electrons, and because of that, because it's got that greater pull, because it hogs the electrons a little bit, hogs those negative charges. What happens is you kind of end up with this kind of partial negative charge on the oxygen end of the molecule and a positive end on the hydrogen sides of the molecule. And you get these poles, these positive and negative poles, the opposite sides of your molecule. That would be a polar molecule. Now, sometimes molecules are not having this discrepancy in pull on the electrons. They might have either equal electronegativity, or you also heard him talk about some symmetry. If you look at these diagrams here, hydrogen gas, for instance, you got two hydrogen atoms. They're both going to have an equal pull on the electrons that they're sharing. The oxygen gas, same thing. Bigger molecule, bigger atoms, more pull, but they both are still going to be equal. Okay, and you have this equal and opposite pull for those electrons, and the end result is you've got a nice neutral molecule. Methane, you see the bottom one, there is a difference in electronegativity between the carbons and the hydrogens that they're sharing. The difference being, however, it's all symmetrical, and so it all is going to balance out in the end. And so those molecules are not going to they're going to be nonpolar molecules. You're not going to have a positive or negative end to it. So in quick summation here, nonpolar molecules, like in the hydrogen we saw, again, equal sharing. Okay, those electrons essentially are halfway between, as it says there, both of the nuclei. With water, for instance, unequal sharing. The oxygen is more electronegative, and so it's going to hog those electrons a little bit more, and so you get a little bit of a net negative charge by the oxygen. And because the hydrogens have those negatively charged electrons less, they get a net positive charge. Now, one of the other things that he alluded to in here was the idea of, with the butter and the water, trying to wash your hands. And we probably all had this experience. Maybe you got oil on your hands and so forth, and you try to wash it off with water. It doesn't work very well. Okay, because oil is a non-polar molecule and water is polar, and they don't really mix. They don't want to get it to have anything to do with each other. Okay, and we get this phrase we hear called like dissolves like. And what that's really saying is that polar solvents will dissolve other polar molecules, polar solutes, or they will also dissolve ionic compounds. The reason for that being the electrical charges can interact. Okay, water is for instance, is a polar solvent. It is happy to dissolve things like salt, which are ionic compounds, or sugar, which is another polar molecule, because they have those different electrical charges that the poles of the water can interact with. Non-polar solvents, they not so much. They're not going to interact. Like you see, you get those layers between the oil and the water. Now, if you have oil on your hands, for instance, and water isn't working very well, you certainly can use a non-polar solute to clean that off a lot better. Um, I'm not recommending it, but certainly if if you ever would use gasoline, for instance, it's going to wash right away. Gasoline's going to dissolve that oil from your hands immediately. It's going to dissolve it really quite well. If you get like maybe sometimes you get like pine sap or something in the summers on your hands, and it doesn't come off very good with water. Use like baby oil or something like that. Again, a non-polar solvent can help dissolve those non-polar solutes. So that's what that phrase "like dissolves like" means. Um, and so what we end up having then, this whole idea when we have a molecule that is held together by a covalent bond, they're sharing electrons. If they share equally, going to be a nonpolar molecule. But if they don't share equally, what you get is a polar molecule that's got a positive end and a negative end. Uh, Quick quiz today. Hope you have a great weekend, and we'll see you next week.